And so eventually, continuum hypothesis was shown to be independent from ZFC axioms, as we've mentioned. So how does that make you feel? And what is independence?
Well, one
and
should
what does
tell
that mean?
the story. The historical story is
Yes.
really quite
Yeah, it's
dramatic,
great.
I think, because Cantor poses the question, late 19th century.
Mm-hmm.
And then it's totally open. Hilbert asks about it, at the turn of the 20th century. Nobody has any clue. There's no answer coming. Until 1938, this is 4 decades later, right? So a long time. And Kurt Gödel proved half of it. What he proved is that if the axioms of set theory are consistent, then there is a set theoretic world where both the axiom of choice and the continuum hypothesis are true. So what he's doing is showing, this is called the constructible universe, Gödel's L. So he solved, this is the same result where he answers the safety question of the axiom of choice, but also for the continuum hypothesis. They're true in the same set theoretic universe. So if ZF without the axiom of choice is consistent, then so is ZFC plus the continuum hypothesis is the result. 1938. It's really such a beautiful argument. It's just incredible, I think, because he's building an alternative mathematical reality. That's the structure of the proof, is that, okay, if there's any mathematical reality, if there's any set theoretic world, then we're going to build another one, a separate one, a different one, maybe different. Maybe it's the same as the original one. It could be. If we started already in the one that he built, then it would be the same. But there's no reason to assume it was the same. So he has this kind of model construction method to build this alternative set theoretic reality, the constructible universe. And then he proves that the axiom of choice is true there, and also the continuum hypothesis is true there. And it's just amazing. Really beautiful argument. Okay, so then for the other part of the independence, that's only half of it, because Gödel shows basically that you can't refute the continuum hypothesis. But that's not the same thing as proving that it's true. He showed that if set theory is consistent without the continuum hypothesis, then it's consistent with the continuum hypothesis. So that's not the same thing as proving that it's true. And then it didn't come until 1963 when Paul Cohen invented the method of forcing and proved that if there's a model of set theory, then there's a model of set theory in which the continuum hypothesis is false. So Cohen also is giving us this extremely powerful tool for building alternative mathematical realities, is how I think about it. He's explained to us how to take any set theoretic world and build another different one in which the continuum hypothesis is false. The forcing extension.
It's just such a fascinating technique, tool of forcing. Maybe I'm anthropomorphizing it, but it seems like a way to escape one mathematical universe into another, or to expand it, or to alter it. So to travel between mathematical universes. Can you explain the technique
Yeah,
of
exactly.
forcing?
It's all those things. It's so wonderful. I mean, that's exactly how I think about it.